Okay. So, yeah, good evening, one and all. I welcome you to the fourth live session. I'm extremely sorry I have written third live session here. It's actually the fourth session of this particular NPTEL course titled Oil Hydraulics and Pneumatics. The tutor for this particular course is Professor Somsekhar Sirama in the Department of Mechanical Engineering at IIT Madras. I am a teaching assistant for this particular course. I'm Arnav. So I hope that you have gone through the videos of the previous weeks and have attempted the assignments. So in today's session, I will be uh, taking up the topic on pumps. We will solve a few basic numericals related to pumps. So accordingly, we will delve into the fundamentals like what are the design parameters, what are how do we select pumps based on specific applications, and a little bit on compressors, like processing of air in the pneumatic systems. So we will look into that a little bit. If you're having any doubts, you can stop me then and there, and you can ask any question, or you can also we can also discuss it after the session is over. Okay, so let's move into the first question. So let's start from one of the most pertinent challenges experienced in the industry. So as Bongani said that he wants to design hydraulic and pneumatic systems for various industrial applications. So you should consider the challenges that you may be facing while designing, while operating such systems, so that such things are taken into the design considerations, and accordingly you take the precautionary measures. So cavitation is one of the most, you can't ignore it completely, but yeah, it is very much detrimental to the hydraulic components. I was looking up to put a photo of impeller that was damaged due to cavitation, but I eventually forgot to put it here. Anyway, you can look it up in Google, and it's pretty much, you can see how the damage is evident due to cavitation. So, what is cavitation? So, before going into the question, can Lokesh or Pungani can unmute yourselves and tell me what do you mean by cavitation? It's one of the most basic phenomena in pumping or in hydraulic pumps. Now, what is cavitation? Bongani,
Sir?
yeah. What do you understand from the term cavitation?
Oh, cavitation. It is when the chemicals or the hydraulics or fluids that are used to work in a system, when they start to build up, forming layers inside the pneumatic or the hydraulic system, then we say that they are cavitation. They are the build-ups, the layers that build up inside the system.
It is not actually layers, but yeah, it doesn't have anything to do with the layers that you are saying. Yeah, I think Lokesh has tried to answer it. It's close to it, but yeah, he's telling bubble formation. So basically, bubble formation is not cavitation. Okay, so what happens? Like if you have a hydraulic pump, say, so so this is the symbol of a hydraulic pump. At the inlet side, you have a pressure P in, and at the outlet side, you have another pressure P out. And this delta P is the head against which the pump is running. It is trying to push fluid from inlet to the outlet side. So, what happens if this particular inlet pressure, for some reason, goes below the vapor pressure of the particular liquid, of the particular hydraulic liquid? It can be oil, it can be water. Then what happens? So, as you all know, if pressure falls down, the uh, vaporization tendency also increases. The liquid tends to vaporize. So, what happens? Like if this pressure falls below the vapor pressure of that particular liquid, then bubbles start forming. So, as the liquid gets converted into its vapor state, then bubbles will form. So, this is the first part of it. And but this is not entirely cavitation. So, what happens? These bubbles start accumulating at the inlet side inside the pump, and that is the low pressure side. So the bubbles keep on growing because the pressure outside is low. And what happens as they're going towards the outer side, there the pressure is increasing. So here pressure is much greater than this particular vapor pressure, right? So what happens? The bubbles are ex- exerted upon by pressure from the outward direction. So its volume tends to decrease, but the air trapped inside it, uh, like the molecules come close to each other, and at a particular point, what happens? It implodes. So due to the implosion of the bubbles, there are shock waves or pressure waves that go and hit the impeller blades or the housing. So this causes the damage. There's also another phenomena. If you go a little bit deeper, like suppose this is my bubble. So if suppose there is a rupture here at any portion due to the impinging pressure acting on it, what will happen? The liquid that is present around it. This is inside this we have air. The liquid around it will try to jet in through this particular hole, and it will go and impinge upon the surface here. So this high speed jet of liquid is also responsible for causing pitting action on the surface over which this bubble is going and hitting. So this also causes the pitting, this jet of liquid. We also call it microjet if the size of the bubble is less. So due to these two, you know, occurrences, what happens? The life of the impeller or the pump, it goes down. So this is the phenomenon of cavitation. I hope you understood. You can ask me if you have any doubt. So in the question, we are asked to identify the probable reasons. So what are the probable reasons of cavitation? So right here, like when cavitation started, we said that the inlet pressure falls below the vapor pressure. That is the root cause of cavitation. So could we do anything so that this condition never arrives? This particular term is constant. We can play around with the P inlet. What we do, we increase the P inlet. Okay, so that it never falls below the vapor pressure. It is always maintained above the vapor pressure of the liquid. So that is one of the remedies, right? Rather, I would say. Acha, the question asks the probable reasons of cavitation. So this is one of the reason that P in is less than P vapor pressure. So undersized plumbing is also one of the reasons. Then positive suction head. So positive suction head means the pressure is greater than the vapor pressure. Okay. So if you are having like the P in minus P vap that is greater than zero, then that is positive suction head. If P in minus P vapor is less than zero, then that is negative suction head. So, under conditions of positive suction head, there is no possibility of the formation of vaporization and bubble formation. But under cases of negative suction head, this cavitation phenomenon occurs. So, positive suction head is not a reason for cavitation; rather, negative suction head is. And low fluid viscosity, generally lower fluid the fluids which are having low viscosity, they are having less tendency of leading to cavitation compared to high viscosity fluids. So again, fluid viscosity is not a possible reason for cavitation. Then clogged lines or suction filters. So if you are having any suction filter here, and that is causing a pressure drop. So suppose you have this P in, and then you have a filter. Wait, let me just clean this up a little bit. Okay, so this is what I had written as P in, and here you have the tank, and the tank is acted upon by the atmospheric pressure. Okay, so what happens like when so here you are having some sort of filter. Okay, so if the filter is getting clogged, then this particular inlet pressure will be reduced. Okay, why? Because there is some pressure drop across this clogged line or the suction filter, and hence the P in will reduce further, and hence the possibility of cavitation will be higher. Okay, so these two are the correct options. Now moving on to the next question. It's also related to this. How can it be controlled or eliminated? How can cavitation be controlled or eliminated? So as we already said, if we can somehow do some like increase this particular P in value, then we can eliminate the possibility of formation of these bubbles. So to do that, generally we maintain a high. Okay, so let's go option by option. So first option says maintain a high suction velocity. So what would be your answer? Well, is this correct, or does this lead to cavitation or does this eliminate cavitation? This option A. What would be your opinion on this? Lokesh or Bungani, can you tell me this high suction velocity is a possible reason for cavitation or it's not? Yeah, you can unmute and answer. Yeah, am I audible? Bongani or Lokesh, can you please confirm if I'm audible or not?
Yes, sir, you are audible, sir.
Okay, okay, okay. Because sometimes when there's some network issue, this may go off, right? So yeah, maintain high suction velocity. So what happens if we maintain at the suction side, and that is in this particular line from where the liquid is being sucked from the tank towards the pump? What happens? Suppose this is your line. Line means basically pipeline. So here the fluid is flowing towards the pump. I am considering atmospheric pressure here. So you see one thing, if I maintain at this point, say, if the velocity of the fluid is high, that is the suction velocity is high, then by Bernoulli's principle, if we do energy conservation, the pressure will automatically be low. Okay, so if we tend to increase the velocity at this point, then the pressure will reduce. And again, reduction in pressure is something that we don't want. If pressure reduces and it falls below the vapor pressure, cavitation will occur. So that's why we need to maintain lower uh, fluid velocity so that the pressure energy component is higher, and the pressure due to higher pressure, the uh, formation of the vaporization phenomena can be neglected. I mean, it can be avoided. So maintain high suction velocity is not the correct option. Rather, this will lead to cavitation. So we have to maintain a lower suction velocity. Okay. Next, shorter inlet lines between pump and the reservoir. Okay. So what would you say on this? If this length of the line, suppose you have your tank here and you have the pump here. So if this distance is higher or this head is higher, then this drop in pressure will be like it would be higher. I mean, the value of P in will be lower. So this particular D has a negative effect on P in. So higher the value of D, less will be the value of P in. So that's why we prefer to use shorter inlet lines. Like D should be less, so that P in should be higher. P in, I would rather say the drop in pressure rather than P in, it should be higher. So yeah, shorter inlet lines between pump and reservoir. So if P in increases, it means it eliminates it avoids the tendency of this vaporization. Next, use low pressure drop inlet filters. Yes, we don't want the pressure to drop in the inlet filters, hence we use low pressure drop inlet filters. Usage of pump for suitable oil as per manufacturer's recommendation. Yes, this is also correct, because we should be knowing like which oil to use under what hydrodynamic conditions. Because if for a particular pump this P in value is going below the vapor pressure of that particular oil, then cavitation is inevitable. So your oil should be such that P its vapor pressure should be less. The oil's vapor pressure should be less, so that the peen can't easily fall below the vapor pressure of the particular oil. Okay, so we had some discussion on cavitation. I hope I was able to explain it. Coming to the next question. So from here on, we will be taking on a few numericals. Okay, so I hope you're acquainted with the pumping theory, how a pump works, and what are the different types of efficiencies that are associated with it. So basically, like if we just look at an overview of it, you have a prime mover, so that delivers mechanical energy to the pump impeller. I'm telling impeller. Impeller isn't the correct, like denomination here. Rather, I would say to the pump, because impeller is used only in hydrodynamic pumps, not in hydrostatic pumps. Next, we have the pump. So the pump is having, so the pump is delivering the energy to the liquid or the hydraulic fluid, I would say. Okay, so you have a few efficiencies that are associated with this conversation. So here you have a few losses which are taken care of by the mechanical efficiency term. And here also you have a few losses which are taken care of by the volumetric efficiency term. Your overall efficiency is a multiplication of this. Okay. So with that, we will try to solve this numerical. A pump has a displacement volume of 100 centimeter cube. So VD is 100 centimeter cube. It's a good practice to convert these things into SI units. Next, it delivers this much, like 0.0015 meter cube per second. So you should be alert about the units that are being given here at 1000 RPM. So you have been said that Q is equal to 0.0015 meter cube per second, and the RPM is 1000. The speed is 1000 RPM basically. So I hope so. This what is this particular discharge? I mean, this is basically delivery, the amount of fluid it and the pump actually delivers. So this is nothing but the actual discharge. I'm denoting it as QA. Then what would be my theoretical discharge? Like, had there been no losses during the pumping of the fluid, so losses again can occur due to a couple of reasons. Like there can be leakages, or there can be uh, due to leakage, or it can happen again. Leakage can happen due to multiple reasons. If the parts get worn off, or if there is some elastic deformation of the parts, then this type of losses come into picture, and that is taken care by this volumetric efficiency term. So QT is basically your nothing but your volumetric displacement, that is the volume of liquid that is displaced per unit cycle of operation of the pump, multiplied by the RPM. Okay, so you have here, right? Okay, so this is given in meter cube per second, and hence you have to convert this minute to a second term. So 1000 divided by 60. So what will this come out to be? Can you just do a quick calculation? I hope that you're also solving along with me. Lokesh or Bongani, what will be the value of QT here once we do this calculation? You can unmute and answer. Okay, so I think I only have to do the calculation, right? Basically, I'm just writing it as 1 by 600 meter cube per second. Now, here comes the volumetric efficiency. So that is nothing but actual discharge by the theoretical discharge. So that is 0.0015 divided by 1 by 600. So 0.0015 multiplied by 600 will give me 0.9. So basically, it's 90%. Next, we are being told that the pressure head against which the pump is pumping the fluid, that is 70 bars. So I'm writing here P is nothing but 70 bars. Basically, this is not absolute pressure. This is the differential pressure. So 70 bars, and you have been given that the prime mover input torque is 120 rpm. So the prime mover uh, is providing an input torque to the pump, and due to this particular mechanical efficiency, there will be some losses, and the output that is being delivered to the pump, that will be less than this input torque. Okay. I'm sorry. I'm sorry. So basically, mechanical efficiency is nothing but your input torque over the yeah, sorry, yeah, it's correct only. It's the output torque over the input torque, right? So the torque that is available here for the pump to rotate, divided by the actual input that the prime mover is delivering the pump. In between that, you have this efficiency term coming up due to different frictional losses and inertial losses. So how to find it? Find out. So you are being given with this particular term here. This is nothing but 120 Newton meter. You have to calculate this T output. So this output means it's an input for the pump actually, but I'm just writing. It's better to write as T actual here. T actual. Okay, so writing it as TA. So TA. Can you tell me what is the formula for that? So TA. How to calculate TA? If we consider the energy that is taken up by the pump from the prime mover and again given out to the hydraulic fluid, that is same. So actual torque at which the pump is um, rotating multiplied by the rotational speed will give me the power that the pump is taking in from the prime mover after all the frictional losses, obviously. So that is equal to the power that is taken up by the hydraulic fluid, right? So delta P multiplied by the Q. So what is this Q? This Q is theoretical Q. That is the theoretical discharge. Again, like I am talking about this particular zone here. Like it is taking up some energy from here and giving out some energy here. So here some losses are occurring and here also some losses are occurring. But along about this interface, if we do this equalization of input and output powers, then it stands out to be like this. So from here we can calculate TA. That is nothing but 70 bars. Again, we have to convert this into SI. So if we convert it into pascals, it will be 10 to the power 5 multiplied by QT. So the value of QT is again 1 by 600. It's already in SI, divided by, you have 2 pi multiplied by N. N is 1000 revolutions per minute. You need to convert it into seconds. Since 1 by 600 is in seconds, so by 60, this will be 1000. So what will be the value of TA or the actual torque? It's coming out to be around 111.41, right? Newton meter. So you can see here, this was the torque that the prime mover was actually trying to deliver, and this is the torque at which the pump is rotating. Okay, so this 111.41. So this the difference. I mean, this particular difference is the mechanical losses. Okay, so from here you will get mechanical efficiency term. That is nothing but this one will be how much? It's coming out to be 0.928. Okay, so the question asks you the total volumetric or the overall efficiency of the pump. So overall efficiency is, what is the value? 0.8355. If we write it in percentage form, generally it's written in percentage, so 83.55%. You just multiply it by 100 and you'll get this in the form of a percentage. What is the next question? What is the theoretical torque required to operate the pump? So basically here the this particular term is the actual torque. Okay, but uh, for this pump to operate at this particular overall efficiency, this much amount of torque is required at the input side. So that is only your theoretical torque. Okay? 120 Newton meter that is consumed, and available torque is 111.41 Newton meter. And from there, you will be getting your overall efficiency. Okay. Next, a vane pump is to have a volumetric displacement of 115 centimeter cube. It has a rotor diameter of 63.5 millimeter, cam-ring diameter of 88.9 millimeter, and vane width of 50.8 millimeter. What will be the eccentricity? So I hope this is just direct numerical. So basic construction of a vane pump is like this. So this is the cam-ring, and this is the rotor, and you have some slots that are made around the periphery like this, and the vanes are like mm, yeah. So this is rotating. Okay, this rotor is rotating, and this particular distance between the center is your eccentricity. And as we already discussed in the previous class also we took up a similar numerical. For practice, we are again doing once again. So this is your inlet, since the volume is expanding, and this is your outlet because the volume is getting compressed here. So the liquid is getting ejected from here. So as you can understand, if this E is increasing or decreasing, accordingly, the amount of liquid that is being uh, displaced through this pump will also get varied, because this space here that is getting influenced by this eccentricity value. Okay, so your eccentricity influences your volumetric displacement. Okay, now it is asking like what is the value of eccentricity such that you have a volumetric displacement of this one. So if we go to the formula of theoretical volumetric displacement, VDT, so that is nothing but pi by 4 dc plus dr into twice of eccentricity into w. Again, this derivation is very easy. You can check the lecture videos, like how we arrive upon this particular equation. This 2 is nothing but, like, if we write instead of E, we write E max, then this particular uh, displacement will be maximum displacement. In that case, this dc minus dr is your dc means the diameter of the cam ring and the diameter of the rotor. That dc minus dr is your maximum eccentricity. Like, okay, so from here, if we just substitute the values, and let's convert all the terms into centimeter. Pi by 4 into dc plus dr. So 6.35 plus 8.89 E into W is 5.08. What will be the value of E here? 115 divided by pi, 6.35 plus 8.89. Okay, and divided by 5.08 divided by 2. So I'm getting 0.945. Okay, I'm getting this particular value. So this is again in centimeters. If you convert to mm, it will be 9.45 mm. So just to check if this is correct or not. This is 115 centimeter cube, and you have this pi by 4, 6.35 plus 8.89. Pi by 4, 2 into 50.8. So 5.08, 121.60. Yeah, this is correct. So in millimeter, it will be 9.45 mm. Okay. If you're asked to calculate the maximum volume, okay, so this if this is a variable displacement pump and you have the option of changing the value of E, then if you're asked what is the maximum volumetric displacement possible, in that case, you can substitute this particular formula here, like this particular value here, and accordingly we'll get VD max. That is for variable displacement type fan pump. Okay, so moving on to the next question. Again, this is also numerical. This is from axial piston pump. Find the offset angle for an axial piston pump that delivers this much at this RPM. So you are given with Q. Q is 0.0019 meter cube per second, and RPM sorry, the speed is 3000 RPM. The pump has 9 15.9 mm diameter pistons arranged on a 127 millimeter piston circle. So I hope that you are acquainted with the arrangement of piston pumps. So okay, so you have different pistons here arranged on the periphery, piston and cylinders rather. This is one piston, this is second one, this third one, and as you may see that if this is your drive shaft, then what happens from here? The suction will take like if this is rotating like this will also rotate because these two are joined by a universal, coupling. This particular shaft and this particular shaft are joined by universal coupling, so both are rotating. And as a result, what happens? This entire piston system, if we look at the side view, this is also like rotating. These pistons are also rotating. So uh, this particular so the cylinders are rotating and the pistons are they these rotating pistons are also getting reciprocated along the length of the cylinders. So as a result, what happens? Uh, Suction happens at one side, and discharge like at the side where the pressure falls down and the volume increases. That is in this side, and discharge happens where the volume is getting compressed, and yeah, that is how it takes place. So if we see like this, suppose this is rotating like this, then you have the suction happening here and the discharge happening in this side. I mean, it would be better to show like this, like if they're generally they're inlet and outlet sides. So from here to here, the volume, if this is rotating like this, from here to here, the volume is increasing, right? So from this side, your uh, liquid will get sucked in. But while it's going from here to here, the volume is decreasing, and hence the liquid is moving out from here. So it's better to show like this, in and out. Okay. So yeah, this is just a basic construction. I haven't drawn it accurately, and this is your drive shaft. It's connected to the prime mover, basically. And here inside this, you have the hydraulic liquid that is being pumped. Okay. So this is the angle theta, and it is one of the important. This is basically called the offset angle, and is one of the most important parameters because this theta determines how much stroke. And why I am telling stroke, that I will just explain, because this is basically the stroke. Stroke is the length by which the piston is expanding or retracting. right? So that particular stroke S, and is the maximum extension of the piston. It is determined by this value theta. So if we just look into it in a simplified manner, suppose this is your out one shaft and this is another shaft, and this is the theta, and this distance is this particular pitch circle diameter of these pistons. The pistons are arranged around this particular circle, and that is basically called the piston circle. So if I'm denoting it by the term D, then we will see that this particular S is nothing but this distance in this triangle. This is the maximum stroke of the piston, or the stroke of the piston, not maximum. So you can see from here that tan theta is nothing but S upon D. So we will be using this particular equation. But before that, we need to calculate both S. We should be knowing both S and D. In the question, you are given with this value D. D is nothing but 127 mm. But you are not given with S. So how to calculate S? From this particular displacement term, that is the volumetric displacement term, you will be able to calculate S. Okay, so this is not volumetric displacement, this is discharge. To calculate displacement, you need to use this RPM value. So your volumetric displacement is nothing but Q upon N. So volumetric displacement is the amount of liquid that is getting displaced per cycle, and Q is the amount of liquid that is getting displaced per unit time period. So this is per second and this is per cycle. So if you divide it by the RPM, that is the revolutions per second or per unit time, then you will get the displaced volume per cycle. Okay, so that is 0.0019. Again, we have to be careful about the units here. This is meter cube per second. So you have to convert this 3000 into seconds. Okay, let's keep it like this. So it will be mm, sorry, meter cube, not mm cube, meter cube. Next, what do we need to do? Hmm. Next, okay, so we also know that from the geometrical considerations, that this volumetric displacement is nothing but the area of the piston. So, sorry, the volume of the piston, each piston multiplied by the number of pistons. So, not piston, rather, sorry, the cylinder, the expanding volume, the expanding and the contracting volume. So, this particular blue color that I have shown marked here, sorry, this particular blue, oh, this blue color that I have marked here, that is the displaced volume for this particular cylinder. So that multiplied by the number of cylinders, that is 9. It has 15.9 mm dia piston. So this dia is given as 15.9 mm. So from here you can calculate the area, cross sectional area, that is nothing but ID square by 4. And if you multiply this area with the stroke length, that is S, this particular S that I have noted here, that will be the stroke volume, right? Stroke volume per cylinder. When you multiply it with capital N, sorry, when you multiply it with small n, then you get the stroke volume for the entire system for n number of cylinders. So that is nothing but your displaced volume. So here, if you write A into S multiplied by small n, that is your total displaced volume. Okay. Now the calculation is pretty much simple. So from here you will get pi d square by 4. So pi into d is 15.9. So it's better to convert it into meter. So 15.9 divided by 1000 square divided 4 by 4, that is area, multiplied by s. S is your stroke length. So s, yes, s we need to calculate, and multiplied by 9. And vd we already got here. So from equating this to, we will get s is equal to how much? Okay, let me simplify the terms. 0.0019 divided by 3000 by 60. So we'll get 10.00038 multiplied by 4. I'm just writing the final answer. Okay. So this multiplied by 4 divided by 9 divided by 15.9 by 1000 divided by 5. So I'm getting around 0.021, 0.021 meter. If I convert it into millimeters, so that will be 21. Basically, it will be 21.26 mm. Okay. Just checking it once again. I multiplied with 15.9 by 1000 square divided by 4. Wait, I think I made a mistake here. So 0.0019 divided by 2060. That's okay. Oh, it's correct. Okay, so it's 21.26 mm only. Next, once we have gotten S, we will just use these equations to calculate the offset angle, that is theta. We already know D is nothing but 127 mm. Okay, so your tan theta is basically S by D. So shall we close today's session, or you have any doubts? We can take it up now. Am I audible? Hello? Yeah,
Hello,
Manjunath.
sir.
Yes, yes, Manjunath. Tell me.
Sir, I missed out some classes, sir. Shall I? Where I get these classes in the website, sir?
Okay, you have enrolled for the course in NPTEL, right?
Yes, sir.
Yeah. Have you enrolled for this particular?
Yes, sir. I enrolled that one.
So there you can find there's a link for. Wait, I am telling you. Do you have this portal opened? So I am NPTEL. Do you have it opened in front of you? You can open it. There you have the live videos section. Okay, if you click there, you will find that will direct you into an Excel sheet, and in the Excel sheet you will get the YouTube links for these videos, these live sessions. You can check it up there,
Okay,
or
sir.
you can directly search on YouTube live sessions on NPTEL course Oil Hydraulics and Pneumatics. So
Okay,
it's
sir.
my channel only. You can find it there. Yeah.
Okay, sir.
Okay. So next class we will be discussing more on pneumatics, the different pneumatic components. It will be mostly theoretical, but I will try to include few numericals from the process thermodynamics if possible, and if that is within the scope, obviously. And Mm, I will see if we can discuss few more problems on pumps, because pump is a very important component, as you may understand, in hydraulics. And you can expect, like from examination point of view, you can expect questions from pump, numerical questions. Okay, so you are expected to practice such numericals for exam if you writing the exam. Okay, thank you for attending the session. So let's close.